Okay, our very last section, 8-5, is the conservation of energy. It's pulling it all together at last. So, first to consider this, we could imagine a descending climber, right? They've done a great job climbing up this rock, and now they want to descend, and they have all this potential energy, but where does it go? Does it become all kinetic energy till they hit the ground? Ideally, no. In this case, it's not elastic the way our bungee was. So, does the energy just disappear? No, right? So the key is that the rope is rubbing against the metal rings and there's friction there. So that potential energy can get transferred to thermal energy. So this is a case where thermal energy is actually really good and helpful in converting the potential energy to a safe form of energy for our climber to get back down to the ground. And this brings us the idea that energy transfer between systems can always be accounted for. It's not going to just sort of vanish like smoke. And this is the law of conservation of energy, describing the total energy of the system. So not just the mechanical energy, but all possible forms of energy. So mechanical, thermal, other internal energy. The total energy of the system can only change by amounts of energy that are transferred to or from the system. So if you only have energy transfer through work, then the work done is going to be the net energy transfer, delta E, and that'll be equal to the change in mechanical energy, change in thermal energy, and the change of this internal energy, where internal energy is basically a catch-all term of things that we don't have a good way to describe. You don't need to calculate it, it would be just told in a problem. Now, an isolated system is one for which there's no external energy transfer. There's no outside force that's pushing on things. And for an isolated system, the total energy cannot change. There still can be energy transfers inside the system, right? And so you might have a change in mechanical energy. Maybe that mechanical energy converts to thermal energy, like we saw with our skateboarder on the ramp when we added friction, or the internal energy converts to some other form. Or perhaps most useful, we could consider the mechanical energy at a later instant in time relative to what the mechanical energy was before, minus however much energy these other two forms take, the thermal and internal energies. Right? So our final mechanical energy might be less than our initial mechanical energy if there's friction to subtract away some of it. So the key here is that in an isolated system, we can relate the total energy at one instant to the total energy at another instant without considering the energies at any intermediate times. We can ignore all of the motion in between, which is really, really nice, as you've hopefully started to see with some of the problems on the lab. Now, an interesting side note here is external forces can act on a system without doing any work. So an ice skater comes up to the wall and pushes herself off it, and she's clearly a better ice skater than me because she's able to go backwards without freaking out. But she turns her internal chemical energy in her muscles into kinetic energy. So there's a form of internal energy. The interesting part here is her kinetic energy change is caused by the force from the wall, but the wall is not actually giving her any energy. It's not that the wall suddenly becomes weaker because people pushed off of it. That would be a bit concerning structurally. Instead, her muscles become just a tiny bit weaker, where she would need to replenish them with adding food so they can rebuild. All right, finally, we can expand our definition of power now, where previously it was the energy transfer over time, so the work done per time, but most generally, it's the rate at which energy is transferred by a force from one type to another. So if energy delta E is transferred in some time delta T, our average power can be just calculated with this change in energy divided by the change in time. And our instantaneous power would shrink this down to a derivative, though oftentimes we'll just look at average instead of instantaneous. Okay, well, that is chapter 8 in a nutshell. We really powered through it. So hope you enjoyed, and please ask questions in the discussion. That is all from here.